Hi, in this research, we present a low complex way for decreasing the bit length without any effect on reconstruction in neural video codecs. I am Mohammed, and this is joint work with Barat and Pierre from Interdigital in France. Current state-of-the-art neural image codecs uses two-stage hierarchical variational autoencoder. The second stage of VCIP encodes the side information, where the first stage encodes the main information. Side information defines the distribution of the main information, and the main information is for reconstruction. The aim of the neural codec is to minimize this loss, where it minimizes the sum of main and side information's bit length as well as the reconstruction error. We can simplify this VCIP by this block diagram. For video compression case, two different VCIP can be used. One for encoding motion information, while another is for residual information. Thus, for video compression, the model should be optimized for minimizing following loss, which is sum of bit length of main and side information of motion, as well as main and side information of residual, in addition to reconstruction error. Since neural codec is machine learning model, it suffers from amortization gap, as it is the case for all ML model. The amortization gap exists because model is optimal in average of train set, but not given single test instance. In order to solve this problem, there are many fine-tuning solutions in the literature. Some optimize the latent for given single image, or optimize some part of neural model or entire model. Since those model needs to run more than 1000 epoch length optimization, their encoding complexity is too costly. Even with massive parallelization, their encoding time is around 400 times more than baseline encoding. Amortization gap can be anywhere in the model. However, in this research, we focus on amortization gap on entropy model. This gap can be defined by the difference of bit length if the model entropy model is perfect. It means instead of learned distribution, what if we use normalized histogram of the latent? Here you can see one learned PMF in green line and normalized histogram of the latent in blue bar. As you can see, the mismatch is not negligible, and this mismatch elongates the bit length. First, let's have a look what kind of entropy models are used in neural codecs. Side information is encoded by factorized model where it has F number of learned PMF table. Main information is encoded by hyperprior entropy model where it has S number of zero mean Gaussian PMF with different scales. Thus, entropy models apply this joint probability where negative log of these probabilities are the expected bit length of the certain information. Our solution is to reparameterize the entropy model with a parametric probability distribution, where our new distribution fits on actual latent better as it can be seen in the figure. We need to fit our new parametric distribution to the actual latent histogram and use this new PMF to encode the latent. We also need to add our parameters to the bit stream explicitly. Thus, decoder will read these parameters and recreate new PMF table and decode the bit stream by this new PMF. We use truncated Gaussian mixture model to reparameterize the entropy model. For side information, we use k equal 1, 2, or 3. For this case, we need to encode weights, mean, and sigma of each Gaussian component into the bit stream. Since the main information is already modeled with zero mean Gaussian, we use truncated zero mean Gaussian for main information. In this case, we have just one single parameters to encode the bit stream. In image compression case, first we need to check each PMF table and fit our parametric distribution model to the actual latent. If the gain is worth to encode extra parameter into the bit stream, we replace the PMF with the new one and encode the parameter into bit stream, unless default PMF table should be used. In video compression case, the general flow is almost the same. Again, we replace the PMF with the new one if it is worthful. But we also take the temporal redundancy of the parameter into account. That means, if the previous frames parameter is the same, we briefly use previous frames parameter instead of writing the parameters into the bit stream. If these don't work to replace, again we use default learned PMF tables. In order to encode new parameters and which one is replaced, which one is used with previous frames parameter, we need to use extra bit stream. This bit stream consists of three types of bits. Temporal bits show if the PMF is replaced by previous PMF parameter or not. Replacement bits show if the PMF is replaced by new parameters or not, and parameter bits shows the explicit coding of parameters. We use three recent neural video codec in our test. We use Compress AI implementation of SSF and author's official implementation of two recent models. We measure the performance over UVG dataset. We first measure the ratio of length of 4 different bit stream, where we found that motion information is less than 10% in these tests. We also present gap percentage of each information independently, as well as the total gap for different frame type and also entire video. We measure 4 to the 7% gap in average, and our methods manage to save 2 to the 5% of the bit stream in lowest rate objective shown in the table. We also repeated the test for different rates and present the measured gap as well as our gains in the figure. Please check our paper for more information. Feel free to reach out us. Thanks for your attention.